Welcome to the first chapter in this series. It's linear motion. Motion is the change in position of an object with respect to time and to a reference point. In this chapter, we shall deal with linear motion, and in this first part, we shall first understand various concepts which include distance, displacement, speed, velocity, and acceleration. We shall also look at how to represent motions on motion graphs. Distance and displacement. This athlete is running along a circular track of radius r in a clockwise direction. He starts at point A and finishes at the same point. What distance does he cover? The distance covered is equal to the circumference of the track, 2 pi r. Is there any displacement or change in position when the athlete comes back to A? No. There is no change in position of the athlete because the initial and the final positions are one and the same. Therefore, displacement is equal to 0. Now let's find the distance and displacement when the athlete stops at B, which is geometrically opposite point A. The distance covered is equal to half the circumference of the track, which is equal to pi r, and displacement, being the shortest distance between the initial and final positions, is equal to the diameter of the circle. Therefore, by definition, distance is the actual length of the path covered by a moving body, irrespective of the direction in which it moves. Displacement is the shortest distance between the initial position and the final position of a moving body. It is distance covered in a particular direction. Speed. Speed is defined as the distance covered per unit time. Therefore, speed is equal to distance covered over time taken. Speed is a scalar quantity. The above definition applies to a body moving uniformly over a period of time. However, this is not always the case. It is therefore better to consider the total distance covered over the total time taken. This gives the average speed of the body. Therefore, average speed is equal to total distance covered over total time taken. The SI unit of speed is meters per second. So if a car travels 200 kilometers in 3 hours, rests for 30 minutes and then covers another 150 kilometers in 1.5 hours, we can find the average speed for the journey. Average speed is equal to total distance over total time taken. Total distance is 350 kilometers. Total time taken, including the time of rest, is 5 hours. 350 divided by 5 gives us 70 kilometers per hour. Speed can also be given in meters per second. To convert kilometers per hour to meters per second, we multiply by 5 over 18. And to convert meters per second to kilometers per hour, we multiply by 18 over 5. For example, 18 kilometers per hour is equal to 18 times 5 over 18, which is equal to 5 meters per second. 30 meters per second into kilometers per hour is equal to 30 times 18 over 5, which is equal to 108 kilometers per hour. Next is velocity. Velocity is defined as the change of displacement per unit time. Velocity is also speed in a specified direction. Therefore, velocity is a vector quantity. Mathematically, velocity is equal to change of displacement over time. The SI unit of velocity is meters per second. However, it may also be measured in kilometers per hour. If the displacement of a body is the same at equal time intervals, no matter how small the intervals are, the body is said to have uniform or constant velocity. The velocity of a body at a particular time is referred to as instantaneous velocity. If the velocity of a body is non-uniform, its displacement is given by displacement is equal to average velocity times time, or average velocity is equal to total displacement over total time taken. Therefore, V is equal to S over T, where V is velocity, S is displacement, and T is time taken. Let's take an example. A vehicle moves 40 kilometers due east in 30 minutes and a further 30 kilometers due north in 20 minutes. Calculate A, its average speed for the whole journey, and B, its average velocity for the whole journey. In the solution, average speed is equal to total distance over total time taken. Total distance is 40 plus 30, which gives us 70. Total time taken is 1 hour, which it gives us 70 over 1, which is equal to 70 kilometers per hour. Velocity is total displacement over total time taken. Therefore, S is the displacement. So to find S, we apply the Pythagoras theorem. So we have S is equal to square root of 40 squared plus 20 squared. So S is equal to 50. Velocity is S over T, 50 over 1, which is equal to 50 kilometers per hour. Next is acceleration. In that short motion, what made the bus increase its speed? Why did the passengers jerk? All this happened because the driver changed the speed of the bus. You know that the speedometer of a vehicle gives the instantaneous speed, that is, the speed of the vehicle at that instant. Observe the needle of the speedometer as the bus is moving. We observe that the needle is moving, indicating that the speed of the bus is varying. At times, we observe that the speed is constant, even though the direction of movement of the bus changes. This change in speed or direction of a moving body in unit time is called acceleration. Acceleration is thus the rate of change of velocity. Acceleration is equal to change in velocity over time. A is equal to V minus U by T, where A is equal to acceleration, U is equal to the initial velocity, V is the final velocity, and T is the time taken. Unit of acceleration is meter per second squared. Acceleration is a vector quantity. Depending upon the change in velocity, acceleration can be positive, negative, or zero acceleration. When speed increases with time, then acceleration is positive. It is negative when the speed decreases. A moving body has zero acceleration if the speed is uniform. Example: the velocity of a body increases from 20 meters per second to 40 meters per second in 10 seconds. Calculate the acceleration. U is 20 v is 40 and t is 10. A is v minus u by t. 40 minus 20 divided by 10 gives us 2 meters per second squared. Motion graphs. Now, the variation of distance, displacement, speed, velocity or acceleration of a body with time can be represented graphically. The common motion graphs are displacement time graphs and velocity time graphs. Distance time graphs may also be used to represent motion. Distance time graphs. The distance of a stationary body does not change with time. The graph of distance against time is therefore a horizontal line parallel to the time axis. The distance covered by a body moving with uniform speed changes uniformly at equal intervals of time. The graph of distance against time is a straight line through the origin. If the change in the distance covered increases for equal time intervals, the distance time graph is a curve as shown on your screen. Displacement time graphs. Now, the displacement for a stationary body does not change with time. However, displacement is a vector quantity, and therefore the position of the body may be negative or positive relative to the observer. The displacement of a body moving with uniform velocity changes uniformly at equal intervals of time. The graph of displacement against time is a straight line. The slope or gradient of a displacement time graph gives the velocity of the body. Now, for a body moving with variable velocity, the displacement time graph in this case is a curve. The velocity at point R is the same as the gradient of the curve at R. This is the slope of the tangent to the curve at point R. In this graph, the velocity increases uniformly with time. When the velocity reduces, the curve is the reverse of this one. Once again, the velocity at point P, that is the instantaneous velocity, can be found by finding the gradient or slope of the tangent at P. Velocity time graphs. Now, the velocity time graph for a body moving with uniformly changing velocity is a straight line. The gradient of velocity time graph gives acceleration. In this case, the acceleration is uniform. For a body moving with its velocity changing, that is non-uniformly, the velocity time graph is a curve. The curve is steeper at R than at P, and the rate of change of velocity with time at R is therefore higher than that at P. The acceleration thus increases with time. For an acceleration that reduces with time, the graph is the reverse of such. Here, the curve is steeper at m than at n. Now, for a body moving with uniform velocity, the graph of such a motion is a horizontal straight line. The gradient of the graph is 0, and therefore the acceleration is 0. An important thing to note is the area under a velocity time graph. Now, consider a body starting from rest and moving with a constant acceleration for time t seconds. The velocity time graph for the body is shown on your screen. If the velocity of the body after t seconds is v meters per second, then distance traveled is equal to average velocity times time, which is equal to 0 because the body started from rest, that is 0 meters per second, plus v over 2 times t, which gives us a half vt. The area A under the velocity time graph is therefore the distance covered by the body after t seconds. Measurement of speed, velocity and acceleration using a ticker tape timer. This method is used to determine the above quantities over short distances. This is the ticker tape timer. It is used in experiments to observe motion. It can be used to measure distance, velocity and acceleration. The ticker tape timer has a vibrating arm at one end, of which is a very tiny head. The head strikes at regular intervals. It vibrates at a frequency of 50 or 100 Hz. That is, it makes 50 or 100 complete cycles in 1 second. Carbon paper is placed between the head and a special piece of paper known as a ticker tape, so that each time the head strikes, it makes a small dot on the paper. As the paper moves through the timer, the distance between the dots vary depending on whether the paper is moving at a constant speed, is accelerating or is slowing down. Finding velocity from a ticker tape. We know that velocity of a motion can be determined by the equation v is equal to s over t. In a ticker tape, the displacement can be measured directly from the length of the tape. Time taken can be determined from the number of ticks of the measured length. But you need to know that t is the time taken from the first dot to the last dot of the distance measured. For example, this figure shows a strip of a ticker tape that was pulled through a ticker tape timer that vibrates 50 times per second. Find the average velocity of the motion. This is the tape. The distance from the first dot to the last is 15 centimeters, which means the displacement is 15 centimeters. To determine the time, you count the number of ticks. There are 15 ticks. Time between each tick is 1 over 50 seconds, which is equal to 0.02 seconds. So 15 ticks is equivalent to 0.3 seconds. V is equal to s over t. 15 over 0.3 gives us 50 centimeters per second. Of course, in most cases, the object will be moving at varying speed, which will allow us to calculate its acceleration. Now, we've just seen how to determine velocity. Now let's look at how to determine acceleration. And acceleration can be determined by the equation a is equal to v minus u by t, where a is acceleration, v is final velocity, u is the initial velocity, and t is the time taken for the velocity change. One important thing we need to know in finding acceleration is we need to give attention to the time taken. Finding time taken for velocity change is different from finding the time taken for displacement change. Keep in mind that t is the time taken from the initial velocity to the final velocity, but not from the initial dot to the final dot. So we continue. We say that we can find acceleration using a is equal to v minus u over t. The initial velocity u can be determined by measuring the length of the first tick and dividing by the time taken. The final velocity can be determined in the same way. Usually students won't have problems with this part. Problem arises in finding the time taken. Now there are 5 ticks from the first dot to the last dot. However, these 5 ticks is not the time we want. As we mentioned, time taken is the time between the initial velocity u and the final velocity v. But then, where is u and v? Well, since u and v are the average velocities, they are in the middle of the length we measured for finding u and v. For example, v is in the middle of the 5 centimeters and u in the middle of the 1 centimeter. So the time between u and v is 4 ticks. This is very important in finding acceleration. So the ticker tape in the figure above was produced by a toy car moving up a tilted runway. If the ticker tape timer produced 50 dots per second, find the acceleration of the toy car. So we need to find the initial velocity, final velocity, and the time taken for the velocity change. First dot, time is 0.02 seconds and the displacement is 5 centimeters. So u is 250 centimeters per second. Last tick, time is also 0.02 second and displacement is 1 centimeter, and therefore v is 50 centimeters per second. To find the time taken, we need to find where u and v are. As we mentioned previously, u and v are in the middle of the 2 dots. Therefore, the time between is 4 ticks, which is equal to 0.08 seconds. Substituting u, v, and t in the equation, a is negative 2,500 centimeters per second squared. So it is a deceleration. Another example. The figure shows a strip of a ticker tape depicting the motion of a trolley moving down an inclined plane. Find the acceleration of the trolley. Frequency of the ticker timer is 50 Hz. So initially the trolley took 5 ticks to move 5 centimeters. The displacement is 5 centimeters and the time is 5 ticks or 0.1 second. Calculating, initial velocity is equal to 50 centimeters per second. At the end of the tape, the trolley took 5 ticks to move 10 centimeters. Thus, displacement is equal to 10 centimeters and time is equal to 5 ticks or 0.1 second. Calculating v is equal to 100 centimeters per second. How about time between u and v? Where's u and v? Is it still between the 2 dots as previously done? No. Since we used 5 ticks for our calculations of u and v, they must be in the middle of the 5 ticks. Thus, u is in the middle of the 5 centimeters and v is in the middle of the 10 centimeters. If we now find the number of ticks, we see that there are 10 ticks between u and v. Hence, the time taken is 10 ticks or 0.2 seconds. Substituting the values, we have an acceleration of 250 centimeters per second squared. Then we move to equations of linear motion. Now consider a body moving in a straight line with uniform acceleration a, so that its velocity increases from an initial value u to a final value v in time t. The acceleration for such a body is given by acceleration is equal to final velocity minus initial velocity over time. Therefore, a is equal to v minus u over t. Making v the subject of the formula, v is equal to u plus at. Call that equation 1. Then again, the displacement s of the body is given by displacement is equal to average velocity times time. Average velocity is u plus v over 2, and then we multiply by t to get displacement. But then again, v is equal to u plus at, so we substitute v in the above equation. So we shall have s, the displacement, is equal to u plus at over 2 times t. Simplifying that, we shall have 2u plus at over 2 times t. If we simplify, we shall end up with s is equal to ut plus a half at squared. We call that equation 2. Now, from the equation v is equal to u plus at, if we make t the subject of the formula, we shall have t is equal to v minus u over a. Going back to the equation, s is equal to v plus u over 2 times t, and substituting t for v minus u over a, we shall have s is equal to v plus u over 2 times, in place of t we replace with v minus u over a. Multiplying that by opening the bracket, we shall have v squared minus uv plus uv minus u squared, everything over 2a. Continuing, we shall have minus uv plus uv cancels out or disappears. So we shall have v squared minus u squared over 2a. Then when we do cross multiplication, we shall have 2as is equal to v squared minus u squared. Making v squared the subject of the formula, we shall have v squared is equal to u squared plus 2as, and we call that equation 3. Now, these three equations are called the equations of linear motion. And for a body moving with uniform acceleration, any of these three equations can be used depending on the quantities given. Note that for deceleration or retardation, a is a negative and thus changes the positive sign in any of the above equations. Let's take an example. A body is uniformly accelerated from rest to a final velocity of 100 meters per second in 10 seconds. Calculate the distance covered. Now, in any question that has been given, all you need to do is collect the information, and when you get what you have, you are able to determine which of the above equations will apply. So from the question we've been given, u is 0 meters per second. Maybe not plainly, but we know the body accelerated from rest. V, the final velocity, is 100 meters per second, and t is in seconds. From all this data, we don't have any of the three equations that can be applied directly. But then again, we can get acceleration using the first equation first of all. So A is equal to V minus U over T. So we shall have 100 minus 0 over 10 gives us 10 meters per second. Once we have the acceleration, then we can find displacement, or the distance covered, using the equation number 2. S is equal to ut plus a half at squared. Ut 0 times 10 plus a half times 10 times 10 squared, which gives us 500 meters. So the distance covered is 500 meters. Another example, a body whose initial velocity is 30 meters per second moves with a constant acceleration of 3 meters per second squared. Calculate the time taken for the body to come to 90 meters per second. Again, collect the information. U is 30, V is 90, A is 3. We can use the first equation. V is equal to U plus AT. 90 is equal to 30 plus 3t. 60 is equal to 3t. And t is equal to 20 seconds. Motion under gravity. Now watch the ball being thrown up in the air. The speed of the ball decreases as it moves up, and then it's 0 for a fraction of a second. The ball again starts coming down, and its speed increases as it does so. This change in speed and direction produces acceleration. This acceleration is produced due to the force of gravity. That is, force of gravity produces acceleration in all falling objects and is known as the acceleration due to gravity. Free fall. All bodies on or near the surface of the earth experience a force of attraction towards the center of the earth known as gravitational force. This force causes bodies to accelerate towards the center of the earth. This is the acceleration of free fall due to gravity, denoted by g. The numerical value of g is approximately 9.81 meters per second squared. Free fall can only occur in a vacuum, but if air resistance is ignored, all bodies fall with this constant acceleration of 9.81 meters per second squared. In a vacuum, a feather and a stone released from the same height will land on the ground at the same time. It should be noted that the three equations of linear motion of a body under constant acceleration can be applied in free fall because the acceleration is also constant. Thus, the three equations become V is equal to U plus GT, H, height, is equal to UT plus a half GT squared, and V squared is equal to U squared plus 2GH. The motion graph for free fall is shown on your screen. This graph shows that the displacement of the body changes increasingly for equal intervals of time. The velocity of a body released from a height h increases every second by about 10 meters per second. The velocity time graph for such a body is a straight line passing through the origin as appears on your screen. An example: a stone is released from the top of a tower 180 meters high. Calculate A, the time it takes to hit the ground, and B, the velocity with which it hits the ground. In the solution for A, the most appropriate equation is h, height, is equal to ut plus a half gt squared. We have u, the initial velocity, because it is free fall, and this applies for all free falling objects. The initial velocity is always 0. We have h, which is the height, and it's 180 meters. We also know g. We've been given to take g as 10 meters per second. So we shall have 180 is equal to 0 times t plus a half times 10 times t squared. So 5t squared is equal to 180. T squared is equal to 36 and t is 6 seconds. B, the most appropriate equation is the first one. V is equal to u plus gt. V is equal to 0 plus 10 times 6 and it's equal to 60 meters per second. Vertical projection. Now, when a body is projected vertically upwards, it undergoes a uniform retardation or deceleration due to the gravitational pull. The body that slows down comes to a rest and then starts falling with an increasing velocity. The sign of g is therefore negative when the body is rising and positive when it is falling. Therefore, for a body projected vertically upwards, the following equations hold. V is equal to u minus gt. H is equal to ut minus a half gt squared. V squared is equal to u squared minus 2gh. Now, these three equations are very useful in deriving expressions for the following. 1. Time taken to reach maximum height. Now, at maximum height, the final velocity v is equal to 0. So from equation 1 above, 0 is equal to u minus gt, making t the subject of the formula. T is equal to u over g. This is the time taken to reach the maximum height. Secondly, time of flight. Time of flight is the time taken by the body or projectile to fall back to its point of projection. At the end of the flight, the displacement of the projectile is 0. Using equation 2 above, 0 is equal to ut minus a half gt squared. Hence, 0 is equal to 2ut minus gt squared. That is, if we multiply everything by 2. Hence, gt squared minus 2ut is equal to 0. Factorizing t, we shall have t into gt minus 2u is equal to 0. And therefore, t is equal to 0, or t is equal to 2u over g. T is equal to 0 corresponds to the start of projection, while t is equal to 2u over g is the time of flight. Now, if we compare this and this, it means that the time of flight is twice the time taken to attain the maximum height. Finally, maximum height reached. Now, the maximum height is attained when the final velocity v is equal to 0. Therefore, v squared is equal to u squared minus 2gs reduces to 0 is equal to u squared minus 2gh. Therefore, 2gh is equal to u squared. And hence, h is equal to u squared over 2g, where h is the maximum height attained. Finally, velocity of return to point of projection. Now, at the instant the projectile returns to its point of projection, its total displacement is 0. And thus, v squared is equal to u squared minus 2gh reduces to v squared is equal to u squared. Therefore, v is equal to plus or minus u. Plus u is the velocity of projection, while minus u is the velocity of the body falling back. The projectile hits the point of projection with the velocity equal in magnitude but opposite in direction to the one with which it was projected. One example. A marble is projected vertically up at a velocity of 30 meters from the ground. Calculate A, the time it takes to reach the maximum height, B, the time of flight, C, the maximum height reached, and D, the velocity with which it lands on the ground. And we are supposed to take G is equal to 10 meters per second squared. In the solution for A, time taken to reach maximum height is given by T is equal to U over G, which is equal to 30 over 10 and is equal to 3 seconds. B, time of flight is given by T is equal to 2T. Time of flight is twice the time it takes to reach the maximum height, so we shall have 3 times 2, which is 6 seconds. C, maximum height reached is given by h max is equal to u squared over 2g, that is 30 squared over 2 times 10, which gives us 45 meters. Finally, D, velocity of return is given by v squared is equal to u squared minus 2gh. So v squared is equal to u squared, which is equal to 30 times 30, and hence v is equal to square root of 900, which gives us 30 meters per second. Now, next we look at determining acceleration due to gravity using two methods. And the first method is using a ticker tape timer. Now, you can use a ticker tape timer to determine G in the same way we used it to determine A. Only this time, the object whose acceleration is to be measured is dropped vertically downwards. Study the dots and follow the same calculations, that is G is equal to V minus U over T. The second method is using a pendulum. Now, a pendulum is simply a weight suspended from a pivot such that it can swing freely. It moves to and fro about a point and thus shows oscillatory motion. The time taken by a pendulum to complete one oscillation is called its time period, and we can calculate that. Here we have a pendulum and a stop clock. We will count the time it takes to complete 10 oscillations. Swing the ball to one side and leave it.
1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.
Oscillation is a motion that repeats itself regularly. So it took 13 seconds to complete 10 oscillations. So the period t is equal to 13 over 10, which is equal to 1.3 seconds. Shorten the length of the pendulum and again calculate the period.
1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.
Now it took 8.5 seconds to complete 10 oscillations. So the period t is equal to 8.5 over 10, which gives us 0.85 seconds. The period varies with the length of the pendulum. Take various lengths of the pendulum and repeat the experiment. Record your data in such a table as this and complete it. Then plot the graph of t and complete it. Then plot the graph of t against L, that is the length in meters. For a simple pendulum oscillating with a small amplitude, t is equal to 2 pi times square root of L over g, where t is the period, L is the length of the pendulum, and g is the acceleration due to gravity. Thus, t squared is equal to 4 pi squared times L over g, which is equal to KL, where k is equal to 4 pi squared over g. Thus, a graph of t squared against L is a straight line whose gradient is equal to 4 pi squared over g. Hence, g is equal to 4 pi squared over gradient. Find the slope of your graph and use it to calculate g. Today we look at projectile motion. Observe the athlete throwing a javelin. The javelin follows a curved path and lands on the ground. Such objects like javelin that move along a curve determined by gravity and air resistance are called projectiles. The path followed by a projectile is called a trajectory. An object dropped vertically downwards, an object thrown vertically upwards, and an object thrown obliquely upwards are examples of projectiles. In all these cases, the input of air resistance is neglected. The velocity of a projectile varies from place to place. At each point, the velocity has components in the horizontal and vertical directions. The horizontal component remains unchanged throughout the flight. The vertical component changes continuously due to the force of gravity. Thus, the horizontal motion is a uniform motion and the vertical motion is a uniformly accelerated motion. The magnitude of the vertical component is different at different points and is directed vertically downward. When we do calculations for projectile motion, we treat each component independently. The only thing that is common to both the vertical and horizontal components is the time of flight. And we apply the equations of motion. In a projectile motion, range is the horizontal distance from the point of launch to the point where the object lands. An example: a ball is thrown from the top of a building 20 meters high with a velocity of 10 meters per second. Find A, the time taken by the ball to strike the ground; B, the distance from the foot of the building to where the ball strikes the ground; C, the vertical velocity at the time it strikes the ground; and D, the velocity with which it strikes the ground. Take G is equal to 10 meters per second squared. Solution A. We have been given U is 10 meters per second, G is 10 meters per second squared, and height is 20 meters. But then H is equal to a half GT squared, and therefore 20 is equal to a half times 10 times t squared. 5t squared is equal to 20. T squared is 4 and t is 2 seconds. B. Range is equal to ut. Therefore we have 10 times 2, which is 10 meters. C. We are looking for the vertical velocity at the time it strikes the ground. So in this case, we consider the free fall and completely disregard the horizontal displacement and velocity. So for free fall, we take the equation V is equal to U plus GT. U is 0 because it is our free fall. So we shall have V is GT, and it's equal to 10 times 2, which gives us 20 meters per second. And finally D, the velocity with which it strikes the ground. As the stone hits the ground, it has two components of velocity: horizontal, which is 10 meters per second, and the vertical, which we have calculated as 20 meters per second. Remember that velocity is a vector quantity, so we can calculate the velocity at impact using the Pythagoras theorem. So r is the resultant velocity, and so we shall have r is equal to square root of 10 squared plus 20 squared, and r is equal to 22.4 meters per second.
Choose a path, choose a direction, choose your day, choose your hours, choose to network, choose a strategy, choose to create, choose your media, choose to care, choose to inspire, choose to listen, choose to learn, choose to train, choose to compete. Newcastle College, why choose anywhere else?